Good afternoon, ladies and gentlemen. My name is Felipe Gomez. This is Ruth, Quant, and Dillon Watring, and our project is the efficient and easily integrated energy converter. So what we wanted to do is to provide an efficient and reliable form of energy conversion, and we wanted to create a single unit that could be easily integrated for use by a large population and a new application. Our prototype, what it's going to be doing is harnessing a linear force and converting it into electrical energy. This is a timeline of our project. We've been working on this project for a whole year. We've stayed on track even with internships and jobs that we all have, and we were able to finish our prototype in a timely manner to be able to get enough testing done on it. As far as the vision and responsibilities, we all have, each team member had a certain responsibility throughout the prototype and throughout the design that they were mainly responsible for, but we all wanted to always be included in the whole project entirely, so we all have supporting roles throughout the whole project. So our motivation behind our design, we wanted to be able to generate electricity in a clean and renewable manner and make this energy easily accessible and economical to communities. We wanted to be able to, contribute to finding alternate methods of harnessing the natural clean energy and converting it into electricity. And we want to expand our knowledge of real-world engineering issues. In our case, would be the energy crisis. And our prototype, we want to be able to have different applications so we could apply it to stuff like staircases, walkways, and even wave energy.
All right, so we began our project by researching different type of pneumatic and hydraulic energy converting systems and their components. So we started looking at the pneumatic and hydraulic pistons. We started looking at the different valves that we use, such as directional control valves, the ball valves, and check valves. And we also looked into the different types of pneumatic and hydraulic motors, such as the drive piston motors and the vane motors.
We also researched current energy converters and found that they're mainly applied in harnessing wind, ocean, and tidal energy. And so efforts are being made on these systems and in these fields to improve the efficiency and reduce maintenance of these systems. Specifically at the University of California, Berkeley, they have what is called a wave carpet that has a wave with oscillating waves and oscillates pistons on the seabed. And it's a hydraulic energy converter and uses hydraulic fluid to generate electricity. There's another system from the American University of Beirut that is a pneumatic energy converter for a power takeoff system for wave energy conversion. And that was a recent paper published, and we use that as a basis for comparison of our pneumatic energy converter. So we surveyed several standards and took these specific ones into consideration. The ASME Performance Test Code, ETC 28 from 2011, is a hydraulic energy efficiency standard that this provided us the procedures and how we would measure the energy efficiency of the system. And we use the ISO International Classifications for Standards for both the system level standards and component level standards. The ICS 93160 and 27140 were for the energy construction, the hydraulic energy construction of our system. And then for ICS 23, it was a fluid systems component standard for the valve specific. And so for our first conceptual design, we initially wanted to go with a strictly hydraulic energy converter with these four main components: the hydraulic piston, the directional control valve, the hydraulic motor, and generator. And it would be something similar to this, a closed loop system that would generate an energy output for each energy input.
So as we began to do more in-depth research of hydraulic and pneumatic systems, we found that the pneumatic would be much more viable for our application for a couple of reasons, like cheaper and easily attained. So we came up with a second conceptual design that's very similar to the first one, except for basically it's just pneumatic instead of hydraulic. But it would have a pneumatic motor, a vane motor, and then a generator. But ultimately, we wanted to come up with a third design that would actually be able to store the compressed air in an air tank. So we came up with a system that basically has the pneumatic piston that compresses the air across the check valve into an air tank where it can be stored until the energy is desired. And then a ball valve can be opened, which would drive the pneumatic motor, and then ultimately drive the generator.
So when we built our design, we wanted to have a prototype that could actually be, it would be as portable as we could possibly make it. So we tried to make it 3 foot by 3 foot by 3 feet, tried to keep everything, as you can see, all the components all enclosed. When we built all our components and everything in SolidWorks, and we ran our simulations through there, and when it came time to actually do the testing, we used the National Instruments LabVIEW MyDAC that you'll see in the video later, so we could be able to calculate the electricity due to time.
The alternate designs for our prototype and design would be based on the application it would be implemented in. So ultimately, the internal configuration would vary only slightly, but keeping all the components in this single unit. And the alternate design would be based on the piston itself, and that would be depending on whether it'd be harnessing a wave energy or used as a staircase or a walkway, and then it would have something more planar to on top of the piston.
All right, so here's a SolidWorks rendering that we did of our proposed design. You can see the pneumatic piston, which goes through an air hose to the check valve into the air tank itself, and then we have a pressure gauge and a pop-off safety valve on it. That's to ensure that the pressure doesn't get above our 120 that we're going for maximum, and then a ball valve that could be released to drive the air across the pneumatic motor, which would spin the generator.
So when we ran the SolidWorks simulations on our parts, we tried to use more of a worst case scenario that we could possibly do. So since most of our components have a max, they have a max pressure of 120 psi. That's the parameters we set. And when we ran the simulation, we used fine mesh, and we did a fixture on the thread so we could simulate an internal pressure.
All right, so when we just quickly look at the results of the simulations, we see that the maximum stress that we see in any of the components is around 13 megapascal, which is well under the yield and ultimate strength for both the brass and the 304 stainless for the components that we used.
So the criteria we used to construct this prototype was using that max working pressure of 120 psi to validate the material we selected, as well as keeping all the component sizes uniform to reduce fittings and keeping all the piping and components at a 1/4 inch NPT, National Pipe Thread, and also having an economic aspect of how we acquired all our parts. So we maintained an affordability initiative to make sure that our prototype could be built at as low cost as possible while still reaching our efficiency goals. And ultimately, we wanted to have ease of assembly and disassembly for our prototype so that it could be require minor maintenance while out in the field. We acquired most of the parts and purchased parts from McMaster-Carr as well as Lowe's Home Improvement while maintaining the criteria I mentioned before. And we had the donated part of the pneumatic bay motor, and we built it from our initial parts acquired.
So when we built the prototype from the initial proposed design, we actually ran into a problem that we had to adjust. So initially we had the piston going directly into a check valve and then going directly into the air tank. And then what happened was basically that was allowing for air to go one direction, but there was no air being allowed to return to the air hose. So it was basically creating a vacuum in the air hose and wasn't allowing for the piston to return to its original position. So how we solved this was we added stronger compression strings to the piston, and then we also added an additional T and a check valve to where it would allow for air to return into the actual air hose. So when we look at the cost, our total predicted cost without the pneumatic motor, which was donated, was about $266. And then our actual cost was about $346. So this additional cost came in from the fact that we had to buy the additional check valve and the T-joint, and then it also came from the air tank, which was a little more expensive, and we had to buy a little bit bigger one because the original one we had planned on using became unavailable. And then our total predicted cost that we were looking at for the whole unit was about $500 to $700, depending on which pneumatic motor you actually select. So here's pictures of our final prototype design, as you can see here. You can see that it has an additional pressure gauge and pop-off safety valve because those came built into the actual tank itself. And then on the right, you can see that we used the pneumatic motor and mounted it to the DC generator by use of a drill chuck.
So we had three main experiments that we did for our prototype. For the first one that we did, we wanted to see how we wanted to calculate how much pressure we could build inside due to a certain amount of cycles that we would pump. One cycle means one pump on the tie rod, and we did that experiment 5 trials, and we did that experiment in 5 trials.
We also ran a second experiment to see the operating time of our system, and so with a certain number of cycles in it, with a 100 cycle interval, we tested the operating time of a fully open valve to run our system.
And then the third experiment that we performed was to determine the voltage and measure the voltage output that we're actually getting from the DC generator, and how long the system actually operated for.
So for the first, this is the results for the first experiment like I was speaking about. We did 5 different trials, and we increased the cycles by 50 each time to see. And as you can see, our numbers stay fairly consistent, so it means our numbers are repeatable. And this is a graph of just the average pressure versus the cycles of how many pumps. So from this, what we were able to do is get this prediction formula that we would be able to predict the pressure that we'll be able to store due to the certain amount of cycles that we would be able to pump.
And these are the results for our second experiment, and it has also very consistent times for how long it can run, depending on the number of cycles that we would input into the system. And this is the graphical representation of such data, also giving us a prediction equation. So the more cycles that we would input, we could check how long it can run for.
Alright, and this is just a quick video of us actually recording it running, and then we just use the MyDeck and just use the digital multimeter to record the voltage. And you can see we get about 36, and then it just slowly drops over time, and then the pressure obviously fully goes down. And this is for the fully open. And then when we actually perform the test, we set up a LabVIEW system where we would record and spit everything out in Excel. So this is the average of all 5 trials. When you look at it, we get an initial spike of voltage, and then it just slowly decreases over time. So we also came up with a equation to be able to predict the voltage at any given time. But this, one thing to note about this is it's only for the fully open valve. So basically we can open the valve a little bit less and have a lower amount of voltage, but it goes for an extended period of time. So efficiency of our system is one thing that we had to look at. So we did this by comparing it and looking at how the American University of Beirut did their project and how they analyzed their efficiency. So we wanted to calculate the input power that we actually did into our system, which was the force applied on the piston times the distance divided by the time. And then also we wanted to calculate the mechanical power that was actually being outputted by the pneumatic motor, which was just the angular velocity of it times the torque rating. And then also the electrical power that we were getting from the DC generator, which was the voltage times the current. So when we look at the actual numbers, we get an input power of about 67.8 watts. And then the mechanical power, we actually had to average the power for this one because the angular velocity of the pneumatic motor decreased over time. So we took the average and got about 2.9 watts. And then the electrical power, the same thing with the voltage, it decreased over time. So we got about 2.26 watts. So when we look at the input power to the mechanical efficiency, we get about 4.28% efficiency. So this is expected because all the research that we did on the pneumatic or the vane motors and whatnot showed that this would be where it was experiencing the most power loss in the vane motor itself. And then the mechanical to electrical, we got about 77.93% efficiency. This could be due to just the misalignment of the mounting, which increases the friction and the resistance. So we got an overall efficiency of about 3.33%.
Although that overall efficiency seems seemingly low, we wanted to compare it with the very similar project. And so from the American University of Beirut, they had an input power of 20 watts and were only able to generate 0.5 watts of electrical energy power. So what we wanted to compare was the price also of dollars per watt that it would cost for installation costs. So we were able to generate a 3.33% efficiency, whereas they were only able to generate a 2% efficiency. So we were able to have a higher efficiency at about a third of the cost with $220 per watt for our system, whereas theirs would cost $4,000 per watt for their system. So to improve our design and other future designs similar to ours, we would improve on the motor itself, the tie rod cylinder, the air tank, and the casing. And these components would either have higher ratings and things that obviously would also cost more, but into scale, it could work out to improve the design of harnessing this energy. And ultimately, our design and our prototype was all built on a global aspect. We wanted to have a system to provide electrical energy to underdeveloped areas and have this system be integrated into these areas with our manuals that we have in several languages, as well as the ease of assembly and disassembly and portability that our system can have. And ultimately, we wanted to contribute to the renewable energy design efforts and provide new technologies to our global community.
So, I mean, like I spoke earlier, we've been working on this design for a whole year already, and we've really improved in all our problem-solving skills, and obviously teamwork. We've all been able to teamwork very good and get stuff done on a timely manner. And we just feel like this keeps us more prepared for the workforce, and it shows us that there's always continued learning in the field of engineering.
And so in conclusion, we were able to design an energy converting system as well as build an actual prototype that was both affordable and portable in our tabletop version. And our testing and analysis of our system proved that it actually converted energy as well as improved the efficiency of previous projects. And so future works for our specific prototype and others to come would be to include a waterproof casing for other applications to actually be submerged, or also to focus on one application. And ultimately, it would be to optimize the power supply and voltage supply output that our system can provide to the globe. We would personally like to thank Dr. Ibrahim Kanzel, our senior design advisor, and he also assisted us with the initial idea for our project.
I'd also like to thank Anthony Rajo from the Applied Research Center for donating the pneumatic motor.
And we would obviously like to thank Dr. Tosunoglu for being our senior teacher throughout this whole year.
Any questions?
I guess I'll start. Why didn't you put a second check valve where the second valve is? The valve is in the system.
The ball valve?
Yes.
You mean, to exit it?
Yeah, so that you could, once it hits a given pressure, automatically feeds the system.
Oh, you mean like to control the pressure?
Yeah.
So we just did it based on the ball valve, so we were just basically just where you can open it and
Manually,
supply it, yeah.
But if you wanted to set this up as a system that was in a walkway or something like that, you don't need to be
Opening it.
opening and closing a valve.
It would just be after.
There should be a
certain
check valve
pressure,
there.
yeah. So we did ours more of like a proof of concept and proof that we could improve the efficiency.
How would you improve the efficiency on the system?
How did we, or how did we?
How would you?
How would we?
I mean, you're at 3%.
Definitely.
Obviously, the
The vane
payback
motor.
on that's not great.
Definitely the vane motor. So
Say again?
from the vane motor, the pneumatic motor.
Okay.
So from everything we found, most of the power loss will come from the vane motor itself. So the air basically spinning it we'll be optimizing the vane motor itself or switching to a different motor, such as like a piston motor.
And we were able to improve the efficiency of the similar system by over 50% from there to our 3.3%. So it's a matter of also having this system and prototype within this idea of harnessing energy where otherwise would not be harnessed at all.
Are the hydraulic motors more efficient?
The hydraulic motors are more efficient, but they're also much more expensive.
So why didn't you think about a hydraulic pneumatic system?
So both systems.
It's not a system that you load with a pneumatic side, but it feeds on hydraulic side.
And, I mean, eventually, when we tried, the main reason we kind of got away from the hydraulic a little bit more was because we were trying to, beginning when we were trying to think more of the enclosing and every tall enclosure, if there would be like any type of leak, it would compromise most of, if it was some type of leak with the hydraulic fluid, it would compromise most of the parts of the side. So we kind of moved away from hydraulic from that. That's what kind of moved into pneumatic, because it would have been a little bit just less messier if we were thinking in a concept of putting it somewhere where it's going to be enclosed and be away, and then if it gets a leak, it's just air, not hydraulic. It's really where mostly we stepped away from hydraulic initially.
Thank you.
Thank you.